In this lesson, we'll start with how to describe how far an object traveled. Let's start with an example of a ball moving to the left and the right. We'll keep track of the ball's direction and distance as it moves. So the ball starts by going 5 meters to the right, then another 4 meters to the right, then it switches directions and goes 2 meters to the left, and finally 5 meters to the left. Okay, so how far did the ball travel? One way of describing how far an object traveled is by looking at its distance, where the distance an object travels is the total amount traveled regardless of direction. Distance is the total amount traveled regardless of direction. When we don't care about where the ball is going, or about whether the ball is going right or left or up or down, we say we're dealing with a scalar quantity. Scalar quantity. And a scalar quantity is one in which direction is not taken into account. Okay, so distance, total amount traveled, regardless of direction. Since you don't care about direction, we say it's a scalar quantity. The symbol for distance is a lowercase d, and the standard unit is a meter, m. Now for our example, the ball, so we had a ball, and it traveled 5 meters, then another 4 meters, then it went backwards 2 meters, and then it went back another 5 meters. Okay, so the total distance is just the sum of all those distances traveled. D total would be the first distance, the second distance, the third distance, and the fourth distance. Putting numbers there, the total distance was your 5 meters, add to that 4 meters, add to that 2 meters, and add to that another 5 meters, for a total of 16 meters. But what if we didn't care about all that in between travel? What if all we cared about was where the object started and where it ended? How far was that distance that was traveled? In physics, we call that displacement. So displacement is another way to look at how far an object travels. And displacement actually takes into account direction. Since displacement takes into account direction, we say that it's a vector quantity. So vectors mean direction matters. The symbol for displacement is a triangle, a lowercase d, and an arrow on top of the lowercase d. We're going to break down all those pieces. The triangle in science is the Greek letter delta. And delta means change in. And when you say change in science, a change in science is a final minus initial. As far as the D with an arrow on top, the D with an arrow on top is position, the symbol for position. So putting that all together gives you the definition of displacement. So displacement the definition is actually its symbol. You have the change in position. Change in position. Change means final minus initial, so really displacement is the final position of your object minus the initial position of your object. So that is one way of looking at displacement. That's the official definition of it. So using that definition, let's calculate the displacement of that rolling ball. The initial position, we'll say d with an arrow, initial, was 0 meters. And the final position, d with an arrow final, the final position was the position of 2 meters. So displacement in this case, or displacement is delta d with an arrow. The displacement is the final position minus the initial position. Remember, change is always final minus initial. So your final position was a position of 2 meters. Subtract that from the initial position of 0 meters. Therefore, your displacement was 2 meters. Now, because displacement is a vector, when we give an answer, we must include direction. So we say the displacement was 2 meters to the right, because the ball moved 2 meters to the right at the end of the day. Now there's another way of looking at displacement. So you can also look at displacement as the total amount traveled, but now you're including direction. So direction is going to matter. So displacement is the total amount traveled as long as direction matters. So direction must be included somehow in your calculations. So how do we include direction? Well, if we're going in the upwards direction or north, we're going to say that that is a positive direction. If we go downwards or south, we say that's a negative direction. If we happen to go to the right or to the east, that's a positive direction. And if we go to the left or to the west, we consider that a negative direction. So let's see how that plays into our example. We can say that we have the displacement of our object. That's going to equal the displacement from the first time it traveled, plus the displacement number 2, plus displacement number 3, plus displacement number 4. Now, as a reminder, it went 5 meters to the right at first, plus 4 meters to the right, plus another 2 meters, but this time the direction was to the left. And the last time it traveled, it also went to the left by 5 meters. And now with that direction, what we do is every time we see a direction to the right, we don't need to change anything because the right is a positive direction. But when we see a direction to the left, what we do is we change those numbers to negatives because left is the negative direction. Okay, so when we're adding this up, we're going to say we have a positive 5 meters plus a positive 4 meters plus a negative 2 meters. Why? Because we went 2 meters to the negative direction plus another 5 meters, but that's a negative 5 meters. Why? Because we were going 5 meters to the left, negative direction. 5 plus 4 plus a negative 2 plus a negative 5, that would give you a positive 2 meters. Because the 2 meters is a positive 2 meters, so that was a positive 2 meters, we say we went 2 meters to the right. And notice I'll always put the direction in square brackets after the magnitude or the amount of travel. So to be specific, we say the amount you traveled is the magnitude. But since this is a vector, displacement is a vector, we must also include the direction of travel. So let's look at some examples from your textbook. The ones I'm going to be doing are from Model Problem 1, and these are on page 180 of your text. Part A says, find the displacement vector from position A to position B if position A is 3.5 centimeters and position B is 5.7 centimeters. So you want to figure out what the displacement, delta D with the arrow, change in position, from A to B. So the displacement from A to B. Now remember the definition of displacement. Displacement equals your final position. In this case, if you went from A to B, your final position would be position B minus your position A. Right? Final position B minus initial position A. Okay? So it says position B is positive 5.7 centimeters. We subtract that from position A, which is a positive 3.5 centimeters. So our displacement then, we subtract those two numbers, we'll get 2.2 centimeters. And that's a positive 2.2 centimeters. So we can say that that is 2.2 centimeters. They didn't tell us if we're going right, left, or east, west. So we can just say that's 2.2 centimeters in the positive direction. So we can put the word positive or a capital P in square brackets. And that would be our final answer in that case. For part B, we're going east and west, and it asks for the displacement from X to Y. So we want the displacement from X to Y. Final minus initial position means we're going to subtract position X from position Y. Position Y is our final position, position X is our initial position. So final minus initial positions. Position Y, we're told, is 8.2 meters to the west. We subtract from that position X, which is 6.9 meters to the east. Remember, west is a negative direction. So what I would do is I would say this is a negative 8.2 meters, and I'm going to subtract from that 6.9 meters. So negative 8.2 minus 6.9 equals negative 15.1 meters. Okay, what about a final answer? Keep in mind significant digits, and we're subtracting, and we see there's only one decimal place in our subtraction, so we should have a final answer with one decimal place as well. This is a vector, so it needs direction, and if you're in the negative direction, that means you're going west. So the final answer for your displacement should be 15.1 meters to the west. So part C will be our final example. We have Alonzo walks 0.64 kilometers north, then walks 1.76 kilometers south. What was Alonzo's total displacement? Now, if you went into this with the displacement definition, as in displacement is the final minus initial position, notice the question doesn't give you those values. It doesn't say that Alonzo started at a certain position and ended at a certain position. So we can't really use that definition of displacement. But remember, you can also calculate displacement by summing up the total displacements along the journey as long as you take direction into account. So we can say the total displacement is displacement number 1 plus displacement number 2. So Alonso first walked 0.64 kilometers north. That is his displacement number 1, 0.64 kilometers to the north. Displacement number 2 that we'll add to that is the 1.76 kilometers to the south. How do we add up north and south? Remember, north is a positive direction, so we can just leave 0.64 as a positive number. South is a negative direction, so we'll add a negative 1.76 kilometers. 0.64 minus 1.76 is a negative 1.12 kilometers. Let's check our significant digits. Each of the numbers we used had 2 decimal places, and we're doing addition subtraction, so our final answer should also have 2 decimal places. As far as direction, we're going in a negative direction, so we must have ended up south. So our final answer should say that the displacement was 1.12 kilometers to the south. Okay, so that was the last example. Now it's your turn. When it comes to physics, just like when it comes to math, it is really crucial that you practice. It can all make sense when you do it along with me, but you have to see if you can do it on your own. So for practice, I'd like you to try numbers 1 to 9 on page 181, and I'll post the solutions online so you can check your answers. Thanks.